Well, welcome to Unit 2. This is Section 7.2, where we talk about some properties of light. So how do we see what we see? We have both luminous objects and non-luminous objects. We see luminous objects from the light they emit, like from a lamp, which is a luminous object. We see non-luminous objects because of the light that they reflect. And that's how we can see the different colors from different things. When light approaches some material, it interacts with the material. Some of that light is absorbed. If the material is transparent, it will pass through onto the other side, where we call that the transmitted light. And some of that light is, of course, reflected, which allows us to see the material. So when light interacts with matter, it can be reflected, absorbed, or transmitted if it's transparent. Let's talk a little bit about the reflection of light. So in this picture, we see some light rays represented by these parallel lines hitting a surface, which is this green shape. And then we have the lines being reflected, showing the direction in which the light rays are traveling after it interacted with that surface. But if that surface is perfectly smooth, as we see there, we get a nearly perfect reflection. Light rays leave the surface parallel to each other, just as we have those light rays are coming in parallel to the surface. If the surface is not smooth, such as in this picture below, we have those parallel light rays coming in, but because the surface is rough, the light rays get reflected in all directions. So the colors that we see result from selective wavelength reflection and absorption. Now let's look at this light ray as it's approaching a smooth surface. Whenever we're talking about light, a line with an arrow represents the direction a light is coming in. We call that the incident ray because it's pointing on the surface. Of course, there's many other streams or rays of light, but we'll just look at one. And we always draw a line that's perpendicular. Perpendicular means 90 degrees. So we always construct a line that's perpendicular to the surface. We call that line the normal. So we have the incident ray coming in. It makes a certain angle, theta I, with the normal. And then we see the reflected ray that leaves the surface out along that path. It's an angle theta R with the normal. And so when we're measuring the angles that these rays are making, is always with respect to the surface normal. And again, that's the line that's perpendicular to the surface. And so whenever we have reflection from a smooth surface, the light rays start to obey the law of reflection, which tells us that the angle of incidence is equal to the angle of reflection, or the incident angle is equal to the reflected angle. You can see that here, theta I is equal to theta R. So let's talk a little bit now about how we can get images being formed. We have cases where we can have the incoming light be reflected from mirrors to change direction, for example, into the eyepiece. And in certain cases, when we don't have the reflection occurring from a material, we can have different types of images. For example, if it's not reflected from a mirror, it's called a real image. And this can be viewed or displayed in a location, kind of like on a screen. An image that's played on a movie screen from a projector, not a digital image. And then the ones that we're talking about here, which consist of our mirrors, make up what's called a virtual image, meaning that it's not a real image. So for example, there is a box, light rays leave the box, it hits the surface of the mirror, and then if we can imagine a normal, for each one of those light rays, they reflect. Now the light rays reflect and the person is looking at it, those rays, the person's eyes. The person cannot see the light ray bending. All they can see is a light ray coming from what appears to be some place behind the mirror. And that's how we get that virtual image. So for virtual images, the image appears to come from a location where it's not directly visible. Examples where we get virtual images include plane mirrors, convex mirrors, and concave mirrors. Another characteristic or property of light is its ability to refract. So here we have the light rays approaching a boundary, but instead of reflecting, we're going to focus on the light being transmitted through to the other material at the boundary. Here we have a boundary between air and water. We have the incident ray hitting the boundary, making an theta I, also known as the angle of incidence, with the normal. When we look at what's happening inside the water, though, the light ray, if it went straight through, would be along this dotted line. But that doesn't really happen. The light ray bends, and there's some angle theta r with the normal. That bending is called refraction. Refraction is the bending of the wave as it travels from one material to another. So when the light crosses the boundary at that surface, there's a change in direction. One of the reasons that the light changes direction is really because of the change in the propagation speed of the light. In the case from light going to air to water, we have light slowing down, and that slowing down causes that change that we will see as a change in direction. Moving to a medium with a slower propagation speed, we can have bending, light bends towards the normal. So when we're going from one material to another, and the speed of that wave is slower in the other material, it bends towards the normal, as we see here. The reverse happens if we're going from a material which it's faster in the new material, the light is going to bend away from the normal. So if we reverse it here and we're leaving air and we're going into, leaving water and we're going into air, this dotted line here shows you where the straight line would follow if it didn't undergo any type of refraction. But because it's less dense in air, light can travel faster in air than in water, we have that increase in the angle of refraction. Another case where you'll see some of the effects of refraction is, for example, on a hot day when you're traveling and you can see a mirage up ahead. A mirage is that virtual image or reflection that you kind of see on the road. It looks like a puddle of water on the road, and it reflects some of the sky and some of the trees in the area. And that's all because of refraction. So in this case, we have light rays coming in from the cooler upper surface to the warm air near the road. And when the angle of incidence causes that angle of refraction to be 90 degrees from the normal, the reflected light ray is refracted along, you can think of it as along the water edge. In this case, here if we look at the refracted ray coming in and the refraction that's along the surface, and that's what's going to happen here as well from the colder air to the hot air, it just refracts along the surface. The angle of incidence of the material that results in the angle of refraction of 90 degrees is called the critical angle. So when we have an angle of incidence coming in, but instead of the angle of refraction being some other angle that's less than 90, we have this angle of refraction here being actually equal to 90, being perpendicular to the normal. This angle of incidence is called the critical angle. And if we increase the incidence beyond the critical angle, we get a reflected ray. So it's reflected within the material just because of what's happening at the boundary. And this total internal reflected ray is called total internal reflection. And that's what happens that gives us the mirage, because we have the ray coming in at an angle that's greater than the critical angle, and it reflects back up into the same medium it came from. And so we can't see the light bending, so it'll appear to us the light is actually coming from the ground, which is why it looks like a puddle on the ground. So one of the ways we describe different substances is by what's called the index of refraction. The index of refraction of air is about 1, which is about what you see here, C. C is the symbol that represents the speed of light in a vacuum. And so the index of refraction is the ratio of the speed of light in the material to the speed of light in a vacuum. When we take that light in a vacuum, the speed at which the light travels is 3 times 10 to the 8 meters per second. So the speed of light in air to the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second, gives us just about 1. And then we have all these other ratios that tells us about what the ratio of the speed of light in water to the speed of light in a vacuum will be. We can see that diamond, the index of refraction is really high. That means the speed of light in diamond slows down quite a bit compared to the speed of light in a vacuum. Dispersion and color. Color is what we see when we see light reflected from different objects. So for example, we're looking at some red roses here, and that's because these flowers reflect light that is with a certain wavelength that corresponds to that red color. Now, all electromagnetic waves of the spectrum travel at the same speed, and that speed is the speed of light, 3 times 10 to the 8 meters per second. The only things that vary are the frequency of the waves and the wavelength of the waves, and that's what's responsible for the different colors. Again, our eyes are only adapted to see the visible light, and so we get to see all the different colors of visible light. And that ranges from 7.9 times 10 to the negative 7 meters to 3.9 times 10 to the negative 7 meters, which is pretty much the other way around. So that's the range at which our eyes are visible. Those are the wavelengths our eyes can adapt it to see. All right, so that is the end of some characteristics of light. We are going to continue with some more characteristics of light in the next unit as we start talking about polarization of light. But before we do that, let's look at this picture here, which shows the different colors of our rainbow, the different colors of the visible light spectrum that our eyes can see, and what some of those values are in terms of the wavelength and the frequency. Those numbers there for the wavelength are in nanometers. So we range somewhere between 400 to 700 nanometers. And then the frequency are in terahertz. So we range somewhere between 430 to 750 terahertz. And that's what our eyes can see. All right, so next up, we will talk about polarization.